In the summer of 2007, a graduate student named David Narkovich was sitting in a basement office at West Virginia University, scrolling through 6 years of archived radio telescope data that nobody had ever properly examined. The data came from the Parkes Observatory in Australia, a 64-metre dish that had been quietly listening to the southern sky since the early 1960s. Narkovich was looking for pulsars, the spinning corpses of dead stars that sweep beams of radio light across the cosmos like distant lighthouses. He'd been at this for weeks. The work was tedious. Most of the data contained nothing but static, the faint hiss of a universe that seems, at first glance, to have very little to say. And then, buried in an observation from July 2001, he found something that should not have existed. It was a burst of radio energy that had lasted less than 5 milliseconds. Not 5 seconds, not 5/10ths of a second. 5,000ths of a second, roughly the time it takes you to blink once quickly. In that sliver of time, something out in the universe had released as much energy as the sun produces in an entire day. The burst had arrived at the telescope in a particular way that told Narkovich it had travelled a vast distance to reach Earth, passing through billions of light-years of intergalactic space. And then it was gone. No repetition, no follow-up signal, no second blink from the same direction. Just one flash of impossible light, and then silence. When Narkovich showed the signal to his advisor, a radio astronomer named Duncan Lorimer, neither of them knew what to make of it. It did not match any known phenomenon. Pulsars repeat. Gamma-ray bursts produce signals across many wavelengths, not just radio. Supernovae unfold over days or weeks, not milliseconds. This was something new, a single devastating pulse from somewhere unimaginably far away, carrying a message that no one could read. They published the finding in 2007, and for the next several years the astronomical community treated it with polite skepticism. One burst, one detection, one telescope. Perhaps the equipment had malfunctioned. Perhaps it was interference from a microwave oven in the observatory kitchen, or a spark from a passing truck, or some glitch in the data processing pipeline that had produced an artifact that looked exotic but meant nothing. The phenomenon became known as the Lorimer burst, and for nearly a decade it remained a curiosity. A single data point that refused to fit into any existing category, but also refused to repeat. Tonight, we are going to travel into one of the strangest unsolved mysteries in modern astrophysics. Since that first detection in archival data, astronomers have found thousands more of these signals. They arrive from every direction in the sky. They come from distances so vast that the light left its source when Earth was a young planet, or in some cases before life had appeared here at all. They last for fractions of a second and release energies that dwarf our sun. Some of them repeat, most do not. And after nearly 2 decades of study, after the construction of dedicated instruments and the analysis of terabytes of data, after hundreds of published papers and conference sessions and theoretical proposals, we still do not know what is making them. They are called fast radio bursts. The name is plain, almost disappointingly technical, but the phenomenon itself is anything but plain. These signals represent one of the most perplexing puzzles the universe has handed us in a generation, and the search for their source has become one of the great detective stories of 21st century science. If this kind of slow, deep journey into the unknown helps you think or helps you rest, consider tapping that like and subscribe button. It helps these stories reach others who might need them. And if you're watching in the dark, if you're settling in for the night, know that we have a long way to travel together, through distances you can barely imagine, chasing a signal that blinks once and disappears into the void. Now, let's begin. Picture the Parkes telescope as it was on that July night in 2001, though, of course, no one was paying attention at the time. The dish sits in a paddock of dry Australian grassland, about 300 kilometres west of Sydney, surrounded by sheep farms and eucalyptus groves. It is enormous, 64 metres across, a white lattice of metal panels cupped toward the sky, like a hand waiting to catch something precious. At night, it tracks slowly across the heavens, so slowly that its motion is invisible to the naked eye, following the rotation of the Earth to keep a single patch of sky centred in its gaze. The radio waves it collects are invisible to human perception. They arrive from sources that emit no light your eyes could ever see, the remnants of stellar explosions, the jets of distant black holes, the spinning neutron stars whose magnetic fields are trillions of times stronger than anything on Earth. The telescope does not take photographs, it listens, and what it hears, it records as streams of numbers, voltage readings from sensitive receivers that can detect fluctuations smaller than a billionth of a watt. On that particular night, the telescope was pointed at the small Magellanic Cloud, a satellite galaxy of the Milky Way that hovers in the southern sky like a detached fragment of the main band of stars. The observation was routine, the data was archived, and for 6 years no one looked at it carefully enough to notice the anomaly hidden inside. The burst itself, the Lorimer burst, as it would come to be known, lasted 4.6 milliseconds. If you could somehow convert it to sound and play it back at normal speed, it would be over before you registered it begun. It would be a click, a pop, a momentary crackle in the static, and then nothing. But when Narkovich examined the frequency structure of that signal, he found something remarkable. The radio waves had not arrived at the telescope all at once. The higher frequency components of the burst had arrived first, and the lower frequency components had arrived slightly later, spread out across time in a very specific pattern. This spreading is called dispersion, and it happens when radio waves travel through plasma, the thin soup of free electrons that fills the space between galaxies. Higher frequency light moves faster through this medium than lower frequency light, so over long distances, a single pulse gets stretched out like a rubber band. The amount of stretching tells you how much plasma the signal passed through, and from that you can estimate how far it travelled. When Lorimer calculated the dispersion measure of the burst, he found that it was far too high to have originated anywhere inside our own galaxy. The signal had passed through more electrons than the Milky Way contains along that line of sight. It had come from outside, from somewhere deep in intergalactic space, perhaps billions of light years away. Let me try to give you a feel for that distance. The nearest large galaxy to our own, the Andromeda Galaxy, is about 2.5 million light years away. If you could travel at the speed of light, the fastest anything can move in this universe, it would take you 2.5 million years to reach it. But the Lorimer burst came from much farther than Andromeda. Based on its dispersion, the signal had travelled roughly 3 billion light years, passing through the sparse plasma that drifts between galaxy clusters like fog between islands. 3 billion light years. The light that made up that burst left its source when Earth was about 1.5 billion years old. Life on our planet at that time consisted of nothing but single-celled organisms drifting in warm oceans. Multicellular life was still hundreds of millions of years in the future. Human beings would not appear for another 3 billion years, and in that impossibly distant past, something out there, something we still cannot identify, had emitted a burst of radio energy so powerful that a small fraction of it could still be detected after crossing 3 billion light years of expanding space. That is the scale of what we are dealing with, and that is why, when the Lorimer burst was first announced, many astronomers simply did not believe it. The skepticism was understandable. Science progresses by requiring extraordinary evidence for extraordinary claims, and a single detection from a single instrument is almost never considered sufficient. Instrumental effects can masquerade as real signals. Terrestrial interference can produce strange artifacts in radio data, and the idea that some unknown process was producing these impossibly brief, impossibly powerful bursts from cosmological distances seemed, frankly, too strange to accept without more proof. For years the proof did not come. Astronomers searched through more archival data, looking for similar bursts, and found nothing. They conducted new observations, pointing telescopes at the same patch of sky where the Lorimer burst had originated, waiting for another flash. Silence. The burst had been a one-time event, or so it seemed, a cosmic fluke that might never repeat, leaving scientists with no way to study it further. And then, in 2010, something happened that nearly destroyed the credibility of the entire field before it had even properly begun. A team of researchers at the Parkes Observatory found several more burst-like signals in their data, and for a brief moment it seemed like confirmation had arrived. But when they investigated more carefully, they discovered that these new signals were not coming from space at all. They were coming from a microwave oven in the observatory's kitchen. When the door of the microwave was opened before the cooking cycle had finished, the magnetron inside would emit a brief burst of radio frequency interference. This interference could be picked up by the telescope's sensitive receivers, producing a signal that looked, at first glance, almost exactly like the Lorimer burst. The signals were named peritons, after a mythological creature that cast the shadow of a man, and their discovery cast a long shadow of doubt over the original burst. If a microwave oven could fool one of the world's most sophisticated radio telescopes, how could anyone be sure that the Lorimer burst was real? Perhaps it too was an artifact, not from a microwave, but from some other piece of equipment, some electrical discharge, some glitch that no one had yet identified. The skeptics felt vindicated. The field stalled, and for several more years fast radio bursts remained in a kind of scientific limbo, neither confirmed nor fully dismissed, waiting for the evidence that would decide their fate. That evidence arrived in 2013, when a different telescope, the Arecibo Observatory in Puerto Rico, then the largest single-dish radio telescope on Earth, detected a new burst. It came from a completely different direction in the sky, with a completely different dispersion measure, and it was detected by a completely different set of instruments. And it had the same basic characteristics as the Lorimer burst. A duration of just a few milliseconds, a frequency structure consistent with passage through billions of light-years of intergalactic plasma, and an energy release that defied easy explanation. One burst could be a glitch. Two bursts, from different telescopes, from different directions, with consistent properties. That was much harder to dismiss. And in the years that followed, the detections accelerated. By 2016, astronomers had found nearly 20 fast radio bursts in archival data and new observations. By 2018, the number had grown to several dozen. And then, in 2018, a new instrument came online in Canada that would change everything. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, was not originally designed to hunt for fast radio bursts. It was built to study the large-scale structure of the universe by mapping the distribution of hydrogen gas across cosmic time. But its designers realized that the same features that made it good for cosmology, a wide field of view, sensitive receivers, rapid data processing, also made it an ideal machine for catching the brief, unpredictable flashes that had eluded astronomers for so long. CHIME looks nothing like a traditional telescope. It has no moving dish, no mechanism for pointing at a specific target. Instead, it consists of 4 enormous half-cylinder reflectors, each one 100 metres long and 20 metres wide, arranged side by side in a field in British Columbia. They look like the hulls of ships turned upside down, or like the corrugated roofs of some vast industrial warehouse. They stare constantly at the sky overhead, watching a strip of the heavens as the Earth's rotation carries different patches of the universe through their field of view. Every day, CHIME observes nearly the entire northern sky, and every day it catches fast radio bursts, sometimes several in a single 24-hour period. In its first year of operation, CHIME detected more than 500 bursts, more than all previous searches combined. The trickle had become a flood, and with that flood came something that no one had expected. Not all the bursts were one-time events, some of them repeated. The first repeating fast radio burst had been found in 2016. A source designated FRB 12112, whose bursts were detected by the Arecibo telescope. Over the following months and years, this source flashed again and again, not on any predictable schedule but sporadically, unpredictably, sometimes firing off dozens of bursts in a few hours and then falling silent for weeks. The repetition ruled out any explanation that required the source to be destroyed in the process of producing the burst. Whatever was making these signals, it was surviving the event and doing it again. But the repeaters turned out to be a minority. Most fast radio bursts still appeared only once, flaring up from somewhere in the distant universe and never repeating, at least not in any of the observations that followed. This created a puzzle within a puzzle. Were the repeaters and the non-repeaters fundamentally different phenomena, produced by different sources? Or were they the same phenomenon viewed under different circumstances? Perhaps the non-repeaters were simply repeaters that had not been watched long enough, or whose subsequent bursts had been too faint to detect. As of now, astronomers have catalogued thousands of fast radio bursts. They arrive at a rate of roughly one every few minutes, somewhere in the sky, though most go undetected because no telescope happens to be watching that particular patch of heaven at that particular instant. If you could somehow see radio waves, If your eyes were sensitive to those frequencies, the universe would be flickering constantly with these brief, brilliant flashes, distant strobes in every direction, a fireworks display played out across billions of light years, and still no one knows what is producing them. Let me give you the shape of the problem as it currently stands. We know that fast radio bursts are real. The detections are too numerous, from too many different instruments, with too consistent a set of properties to be artifacts or interference. We know they are extragalactic. They come from outside our Milky Way, from distances that range from a few 100 million to several billion light years. We know they release enormous amounts of energy, at least in the radio band. A typical burst, in its few milliseconds of duration, emits more radio energy than the sun produces in a day. We know that some of them repeat and most do not, at least as far as we have observed. We know that they exhibit complex structure in both time and frequency. Some bursts show multiple subpulses, some show drifting patterns that sweep across the radio spectrum, some show polarization signatures that suggest they are passing through strong magnetic fields. What we do not know is what makes them. And here is where the mystery deepens, because the requirements for producing a fast radio burst are genuinely extreme. Whatever the source is, it must be capable of releasing an enormous amount of energy in an incredibly short time. 5 milliseconds is not a lot of time. The speed of light is roughly 300,000 kilometers per second, which means that in 5 milliseconds, light travels about 1,500 kilometers. For a signal to remain coherent over such a brief interval, the emitting region must be smaller than that, smaller than 1,500 kilometers across. If it were larger, different parts of the source would be firing at slightly different times, and the pulse would be smeared out, no longer sharp and brief. So we are looking for something that is smaller than a planet, that can release as much radio energy as the sun in a day, and that can do so repeatedly, at least in some cases, without being destroyed. The list of candidates is not long. The leading hypothesis, the one that most astronomers currently favour, involves neutron stars, the collapsed cores of massive stars that have exhausted their nuclear fuel and blown off their outer layers in supernova explosions. A neutron star is an object of almost unimaginable density. It contains roughly 1.5 times the mass of the Sun, compressed into a sphere about 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. The matter inside is so tightly packed that it exists in exotic states that cannot be replicated in any laboratory. Neutron stars also possess the strongest magnetic fields in the known universe. A typical neutron star has a magnetic field trillions of times stronger than Earth's, and the most extreme examples, called magnetaires, have fields hundreds or thousands of times stronger still. These magnetic fields store enormous amounts of energy, and under certain conditions they can release that energy in violent outbursts. In 2020, astronomers detected a fast radio burst from within our own galaxy for the first time. The source was a magnetar called SGR 1935 Passatis 2154, located about 30,000 light-years away in the direction of the constellation Vulpecula. The burst was accompanied by an intense flash of X-ray and gamma-ray radiation, the telltale signature of a magnetar flare, a sudden, violent reorganization of the star's magnetic field that releases tremendous energy. This was the smoking gun that many researchers had been waiting for. A magnetar, caught in the act, producing a fast radio burst, the mystery solved. Except it was not quite that simple. The burst from SGR 1935 Pulsen 2 to 154 was real, and it was clearly associated with a magnetar, but it was also about 1,000 times weaker than typical extragalactic fast radio bursts. At the distances of the most distant bursts, billions of light-years away, the magnetar's burst would have been too faint to detect. The most luminous fast radio bursts require sources that are far more powerful than anything we have seen a magnetar produce. Perhaps magnetars are the answer, and we simply have not yet witnessed one at the peak of its activity. Perhaps the most powerful bursts come from especially extreme magnetars, or from magnetars in unusual environments, or from magnetar-like behaviour in objects we have not yet identified. Or perhaps magnetars are only part of the answer, responsible for some fast radio bursts, but not all of them. The possibility remains open that there are multiple types of sources. The repeating bursts might come from one kind of object, and the apparently one-time bursts from another. Young, rapidly spinning neutron stars might produce certain varieties. Colliding neutron stars or neutron star black hole mergers might produce others. Some researchers have proposed more exotic explanations: cosmic strings, the decay of primordial black holes, or even, and this is always mentioned with a kind of nervous embarrassment, extraterrestrial intelligence. The signal itself would be an almost perfect beacon for a civilization wishing to announce its presence across cosmological distances. Brief, intense, detectable, across billions of light years with relatively modest equipment. If you wanted to say hello to the universe, a fast radio burst would be an efficient way to do it. Let me be clear, no serious astronomer believes that fast radio bursts are artificial signals. The distribution of burst properties, the consistency of their energy scales, the association with known magnetar activity, all of this points toward natural astrophysical processes. But the hypothesis has been formally considered because good science requires considering all possibilities, however unlikely. And the fact that it must be considered at all tells you something about how strange these signals are. We're dealing with a phenomenon that exists at the edge of explanation, where the boundary between the plausible and the fantastic becomes difficult to see clearly. For now, the mystery remains open. Each new detection adds data points. Each repeating burst allows astronomers to triangulate a host galaxy, to study the environment around the source, to build up a picture of what conditions are necessary for these signals to occur. The CHIME telescope continues to harvest bursts from the northern sky. New instruments are coming online in Australia, in South Africa, and China. The sample grows, the patterns slowly emerge, and somewhere out there, scattered across the universe like fireflies in an endless dark, the sources continue to flash. Once, twice, sometimes dozens of times, and sometimes never again. They have been doing this for billions of years, long before any telescope existed to notice them. They will continue after we are gone. The universe has always been full of these signals, these brief and brilliant sparks of radio light, erupting and fading in silence. We are only now beginning to learn how to listen. To understand why fast radio bursts are so difficult to catch, you need to understand the vast asymmetry between the size of the universe and the size of our attention. The sky, from any point on Earth, is a hemisphere, half a sphere enclosing you like a dome. But the sky that telescopes must search is the entire celestial sphere, the full enclosure of the cosmos in every direction. If you divide that sphere into patches the size of the full moon, you get roughly 100,000 patches. A fast radio burst occurs somewhere in that sphere, in one of those 100,000 patches, for less than 5 milliseconds, and then it is gone. To catch it, you need to be watching the right patch at the right moment. Most radio telescopes have narrow fields of view. The Parkes dish, for all its size and sensitivity, can only observe a tiny fraction of the sky at any given moment. A single patch, maybe two. The Arecibo telescope, before its collapse in 2020, had similarly limited coverage. To catch a fast radio burst with one of these instruments requires luck. The burst must happen to occur in the precise direction the telescope is already pointed, during the precise interval it is recording data. This is why the early detections were so sparse. It was not that fast radio bursts were rare, it was that our ability to catch them was catastrophically limited. We were trying to detect lightning strikes across an entire planet by looking through a keyhole. CHIME changed the equation by widening that keyhole into a doorway. Its 4 cylindrical reflectors observe a strip of sky roughly 120 degrees long and a few degrees wide, all at once, all the time, every day. As the Earth rotates, different parts of the sky pass through that strip, so over the course of 24 hours, CHIME observes most of the northern hemisphere. Its wide field of view means it catches bursts that narrower instruments would miss, and its continuous operation means it catches bursts that happen in the gaps between targeted observations. But even CHIME cannot see everything. It cannot observe the southern sky. It cannot detect bursts that occur during the few hours each day when its strip of sky overlaps with the sun, whose radio emissions would overwhelm the faint signals from distant sources. And it cannot detect bursts that are too faint, or too brief, or too heavily dispersed by intervening plasma. The bursts that we have detected are therefore a biased sample, the tip of a much larger iceberg. For every burst that CHIME catches, there are dozens, perhaps hundreds, that flash and fade unseen. The true rate of fast radio bursts across the entire observable universe is staggering. Current estimates suggest that somewhere in the cosmos, a fast radio burst occurs roughly once every second. Every second. Not every minute, not every hour, but every second, somewhere in the vast volume of space that our telescopes can theoretically reach, something is flashing. Let that settle for a moment. Close your eyes if you like, and picture it. A sphere of darkness extending billions of light years in every direction, filled with galaxies beyond counting, each galaxy containing billions of stars. And in that darkness, scattered randomly across the volume, brief sparks of radio light are blinking into existence and winking out again, one per second, everywhere and nowhere in particular. A continuous flicker that has been going on since the universe was young and will continue until the last stars die. We have detected a few thousand of these signals, a few thousand, out of the billions upon billions that have occurred in the time since we began looking. Our catalogue is a census of fireflies conducted from a single hilltop on a single night, and the forest stretches to the horizon in every direction, dark and deep and full of lights we have not yet seen. The detection of a fast radio burst is only the beginning of the work. Once a burst is recorded, astronomers face a cascade of follow-up questions. Where exactly did it come from? What kind of galaxy hosts the source? Is the source embedded in a dense environment, a supernova remnant, a star-forming region, a galactic nucleus? And critically, will it burst again? For repeating sources, these questions can be answered with patience. If a source flashes multiple times, its position can be triangulated with increasing precision. The initial detection gives a rough location, somewhere within a region of sky that might contain dozens of galaxies. Subsequent detections, especially if they're captured by multiple telescopes simultaneously, allow astronomers to narrow the position down, first to a handful of candidate galaxies, then to a single galaxy, and eventually to a specific location within that galaxy. The first such localization was achieved in 2017, for the repeating source, FRB 121102. After years of follow-up observations, astronomers pinpointed the source to a dwarf galaxy, about 3 billion light-years away. The galaxy was small, irregular, actively forming new stars, the kind of environment where young, energetic neutron stars might be expected to form. Even more intriguingly, the source itself was located in a compact region of persistent radio emission, as if it were embedded in a dense cloud or nebula of some kind. This was crucial information. It told astronomers that whatever was producing the bursts existed in an extreme environment, surrounded by plasma and magnetic fields. It was consistent with a young magnetar, perhaps only a few decades or centuries old, still embedded in the debris of the supernova explosion that created it. The picture was coming into focus, detail by detail. But localizing non-repeating bursts is much harder. If a source only flashes once, there is no opportunity for follow-up observations. The initial detection must capture enough information, enough precision in the burst's arrival time across different telescope receivers, to fix its position on the sky. This requires instruments with very long baselines, multiple dishes separated by hundreds or thousands of kilometers, acting together as a single virtual telescope through a technique called interferometry. In recent years, these techniques have begun to pay off. A number of apparently non-repeating bursts have been localized to specific galaxies, and the host galaxies turn out to be surprisingly diverse. Some are small, star-forming dwarfs like the host of FRB 121102. Others are large, quiescent elliptical galaxies where star formation ceased billions of years ago. Some bursts seem to originate from the outskirts of their host galaxies, far from the dense central regions. Others come from regions near galactic nuclei, where supermassive black holes churn. This diversity is puzzling. If all fast radio bursts came from a single type of source, say young magnetars in star-forming regions, you would expect their host galaxies to share certain characteristics. But the host population is varied, almost indiscriminate. It is as if the universe is telling us that the phenomenon is more common, more ubiquitous, than any single explanation can accommodate. Perhaps there really are multiple source classes, multiple mechanisms that can produce these bursts, each one contributing to the observed population. Or perhaps the phenomenon is somehow more fundamental, arising from physics that operates in many different environments, under many different conditions. the data is not yet sufficient to decide between these possibilities. There is one more piece of the puzzle that I want to lay before you now, before we pause to rest and let these ideas settle. It concerns the structure of the bursts themselves, not where they come from, but what they look like when they arrive. A fast radio burst is not simply a flash of light. It is a complex signal, carrying information about the environment it passed through, and potentially about the mechanism that produced it. When astronomers unpack the data from a burst detection, they examine several properties. The burst's frequency structure, showing how the signal is distributed across different radio wavelengths. Its temporal structure, showing how the intensity varies over the milliseconds of its duration. Its polarization, showing the orientation of the electromagnetic waves. And its dispersion, showing the signature of the plasma it traversed on its journey to Earth. Each of these properties tells a story. The dispersion measure, as I mentioned earlier, reveals the integrated column of electrons between the source and the detector. The higher the dispersion, the more plasma the signal passed through, and the farther it likely travelled. But the dispersion can also contain contributions from the local environment of the source. If the burst originated in a dense nebula, or near a massive star, the local plasma would add to the measured value, making the distance estimate uncertain. The polarization of a burst is equally informative. Radio waves can oscillate in a particular direction, up and down, side to side, or in a rotating pattern as the wave propagates. The degree and type of polarization carry information about the magnetic fields through which the signal passed. Many fast radio bursts are highly polarized, suggesting they were produced in strong field environments or propagated through magnetized plasma. Some show complex polarization signatures that change over the course of the burst, as if the magnetic field were varying on millisecond timescales. And then there is the temporal structure, the shape of the burst in time. Some bursts are simple, a single spike of intensity that rises and falls smoothly over a few milliseconds. Others are complex, multiple subpulses, drifts in frequency, asymmetric profiles, microstructure within individual peaks. The complexity suggests that the emission process itself is intricate, perhaps involving multiple emitting regions or rapidly evolving physical conditions at the source. All of this data is available for each detected burst. Thousands of bursts, each one a unique snapshot of some unknown process, each one carrying clues that astronomers are still learning to read. The field is young, barely 15 years old. The techniques for analysing burst properties are still being refined. The theoretical models are still in flux, tested against each new detection, refined or discarded as the evidence accumulates. What we have now is a map covered in question marks. The coastlines are sketched in, but the interior remains blank, filled with speculation and conjecture. Fast radio bursts are telling us something about the universe, about the environments around neutron stars, about the plasma that fills intergalactic space, about the extreme physics that governs the most magnetic objects in the cosmos. But we do not yet speak their language fluently. We are still learning to listen. Here is where we rest for a moment. Take a breath. Let the silence settle around you like the silence between galaxies, that vast dark through which these signals have been travelling for billions of years. We have covered the discovery, a graduate student scrolling through old data, finding something that should not exist. We have covered the early skepticism, the microwave oven imposters, the years of doubt before confirmation arrived. We have covered the flood of detections from Keim, the thousands of bursts now catalogued, the repeaters and the apparent one-time events. We have touched on the leading hypothesis, magnetars, those impossibly dense, impossibly magnetic stellar corpses, and the complications that prevent that hypothesis from being a complete answer. But we have barely begun. In the chapters to come, we will travel deeper into the physics of neutron stars, into the exotic matter that makes up their cores, and the extreme magnetic fields that wrap around them like invisible armour. We will examine the environments where fast radio bursts are born, the host galaxies and the local conditions that seem to be necessary for these signals to emerge. We will consider the alternatives to the magnetar hypothesis, the collisions, the cosmic strings, the explanations that sound like science fiction but cannot yet be ruled out. And we will confront the deepest question that fast radio bursts pose, not what is making them, but what they can teach us. Because these signals, whatever their source, are probes of the universe itself, They pass through billions of light-years of intergalactic space, through plasma and magnetic fields and the expanding fabric of space-time. By the time they reach us, they carry the imprint of everything they encountered along the way. Each burst is a message in a bottle, thrown into the cosmic ocean billions of years ago, drifting across inconceivable distances and washing up on the shore of our radio telescopes today. The message is not addressed to us. It is not even a message in the conventional sense. There is no sender, no intention, no meaning beyond the physics that produced it. But it carries information nonetheless. Data encoded in the shape of the signal, waiting to be deciphered by anyone patient enough to listen. That is what astronomers are doing now. Listening, deciphering, slowly assembling a picture of something that was completely unknown to science less than 2 decades ago. The universe has handed us a new phenomenon, a new window into processes we did not know were happening, a new set of questions we did not know to ask. And in the silence between the flashes we wait. Now we descend into the heart of a dead star. Not the soft, familiar death of our own sun, billions of years in the future, when it will swell into a red giant and then shed its outer layers into a glowing planetary nebula, leaving behind a white dwarf, a dense cinder the size of Earth, cooling quietly for eternity. That is a gentle death, a long sunset. What we are discussing now is violence on a scale that defies ordinary language. We are talking about the death of a massive star, a stellar giant 10 or 20 times the mass of the Sun, and the catastrophic collapse that transforms it into something our intuition cannot accommodate. Picture the moment. The star has burned through its fuel, layer by layer, fusing hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage burns faster than the last. The hydrogen burning took millions of years. The silicon burning takes about a day, and then it stops. Iron cannot be fused to release energy. The physics forbids it. The nuclear furnace at the star's core, which has been holding up the weight of the entire star for millions of years, suddenly goes silent. What happens next takes less than a second. The core collapses. Not slowly, not gradually, but in a free fall that accelerates to 1/4 of the speed of light. A ball of matter the size of Earth, containing more mass than our entire Sun, compresses down to something the size of a city, 20 kilometers across. The density increases by a factor of 100 million. Electrons are crushed into protons, forming neutrons. The atomic structure of matter itself breaks down. What remains is not made of atoms anymore. It is made of neutrons packed together so tightly that a teaspoon of this material would weigh as much as a mountain. Let that settle for a moment. The collapsing core hits a wall. Not a physical wall, but a wall of pressure created by the neutrons themselves refusing to be compressed further. This is called neutron degeneracy pressure, a quantum mechanical effect that has no analogy in everyday experience. The infall bounces. A shockwave forms and races outward through the still collapsing outer layers of the star. For a brief moment, hours or days, the shockwave stalls, struggling against the infalling matter. Then, powered by a flood of neutrinos from the core, particles so ghostly that they pass through planets without noticing, the shockwave revives and tears the star apart. This is a supernova. For a few weeks, the exploding star shines brighter than all the other stars in its galaxy combined. The energy released is staggering, more energy in a second than our Sun will produce in its entire 10 billion year lifetime. The outer layers of the star are flung outward at tens of thousands of kilometers per second, seeding space with heavy elements that will eventually become planets and people and radio telescopes. But we are not interested in what is flung outward. We are interested in what remains behind. In the centre of the expanding debris cloud spinning in the dark is the neutron star. Imagine an object with the mass of the Sun compressed into a sphere that would fit comfortably inside any major city on Earth. The surface gravity is 200 billion times stronger than Earth's. If you could somehow stand on the surface, which you could not, because you would be crushed into a film of neutrons in a microsecond. A drop of water falling from 1 centimetre above the surface would hit with the energy of a small nuclear weapon. The escape velocity is 2/3 the speed of light. Light itself, if emitted from the surface at a shallow angle, bends back around toward the star. You can see the back of a neutron star from the front. The surface is a crust of iron nuclei arranged in a crystalline lattice, harder than any material on Earth, stretching over a liquid interior of neutrons and exotic particles that physicists are still trying to understand. The temperature at the surface, even after cooling for thousands of years, might be 1,000,000 degrees. The interior is hotter still, though the details depend on physics we have not fully worked out. And somewhere beneath that crust, in the super-dense neutron fluid, there may be forms of matter that exist nowhere else in the universe. Quarks freed from their confinement inside protons and neutrons, hyperon particles, strange matter. The core of a neutron star is a laboratory for physics at the very edge of what we understand. But all of this, the density, the gravity, the exotic matter, is not what makes certain neutron stars capable of producing fast radio bursts. What matters for that is the magnetic field. When a star collapses, it does not just compress matter, it compresses magnetic flux. The original star had a magnetic field, perhaps similar in strength to the Sun's, threading through its enormous volume. As that volume shrinks by a factor of 1,000,000,000, the magnetic field lines are squeezed together, concentrated, amplified. Conservation of magnetic flux, the same physics that makes a skater spin faster when she pulls in her arms, means the field strength increases dramatically. A typical neutron star has a magnetic field about 1,000,000,000,000 times stronger than Earth's. If you could bring a neutron star close to our solar system, do not worry, there are none nearby, the magnetic field would erase every credit card, every hard drive, every magnetic strip on the planet from the distance of the moon. It would disrupt the compass needles of 1,000 civilizations. But magnetars are different. Magnetars are neutron stars with magnetic fields 1,000 times stronger still, 1,000,000,000,000 times Earth's field, the strongest magnetic fields known to exist anywhere in the universe. We do not know exactly how magnetars acquire these extraordinary fields, whether it happens during the collapse itself, through some special configuration of the collapsing matter, or whether it develops afterward through internal processes we do not fully understand. What we know is that these fields exist, that they produce observable effects, and that they seem to be connected to the most energetic radio emissions we have ever detected. The magnetic field of a magnetar is not passive. It is alive with energy. The field lines are anchored in the neutron star's crust, threading through the interior and extending out into space in complex configurations. And here is the thing about magnetic fields this strong. They do not just sit there, they exert pressure. A magnetic field of 1,000,000,000 Gauss exerts a pressure equivalent to 10,000,000 tons per square centimetre. This pressure deforms the crust. It builds up stress. It stores energy. And sometimes that stress releases. Imagine the crust of a neutron star, that crystalline lattice of iron nuclei, harder than anything we can create on Earth, stretched over a seething interior, suddenly cracking. A starquake. The crust shifts by millimeters, perhaps centimeters. In human terms, this sounds like nothing. But on a neutron star where gravity is 200 billion times stronger than Earth's, and the magnetic field contains more energy than 1,000,000,000 suns produce in a year, a centimetre-scale shift is a cataclysm. The magnetic field, anchored to the crust, is suddenly reconfigured. Field lines snap and reconnect. Energy that was stored in the stressed field is released in a fraction of a second. This is the same basic physics as a solar flare, but scaled up by factors of 1,000,000,000,000. A magnetar flare can release more energy in 1/10 of a second than our sun emits in 100,000 years. We have seen these flares. On December 27, 2004, a magnetar in our own galaxy, an object called SGR 1806-20, located about 50,000 light-years away on the far side of the Milky Way, produced a giant flare so powerful that it measurably affected Earth's upper atmosphere, from 50,000 light-years away, 1/10 of the way across the galaxy. The flash was bright enough that if it had come from a few light-years away, from the distance of the nearest stars, it would have been dangerous, not inconvenient, dangerous. That event confirmed what theorists had suspected. Magnetars are capable of releasing enormous amounts of energy in very short times. The timescales involved, milliseconds to seconds, match the timescales of fast radio bursts. The energy budgets were in the right range. The physical mechanisms, magnetic reconnection, starquakes. sudden releases of stored field energy, could plausibly produce coherent radio emission. And then, in 2020, came the detection that tied everything together. A magnetar in our own galaxy, an object called SGR 1935 plus 2 for 4, produced a burst that was detected simultaneously in X-rays and radio waves. The radio burst was brief, milliseconds long, and extraordinarily bright for a galactic source. If the same burst had occurred in a distant galaxy, it would have looked exactly like the fast radio burst that Keim and other telescopes had been detecting from cosmic distances. The luminosity, the duration, the spectral characteristics, all of it matched. This was the smoking gun the field had been waiting for, a known magnetar in our own galaxy, producing a radio burst with the same properties as the cosmological fast radio bursts. The connection was no longer theoretical, it was observed. But, and here is where the comfort of a simple answer dissolves, this detection raised as many questions as it answered. The burst from SGR 1935 plus 2 154 was bright by galactic standards, but it was still 1,000 times fainter than a typical extragalactic fast radio burst. If the same process that produces bright extragalactic bursts was at work here, it was operating at the low end of its range. Perhaps there is a spectrum of magnetar bursts, with the galactic event representing the dim end and the cosmological bursts representing the bright end. But if so, what determines where on that spectrum a particular burst falls? Why do some magnetars produce modest radio emissions while others produce signals detectable across billions of light years? And then there are the repeaters. Some fast radio bursts repeat. We have discussed this already. Sources like FRB 2012-102A, which has been seen to produce hundreds of bursts over the years. These repeaters are difficult to explain with any model that involves the destruction of the source. A magnetar flare does not destroy the magnetar. The crust cracks, the field reconfigures, but the neutron star remains. In principle, it can flare again and again and again. This makes magnetars plausible candidates for repeating sources, but the statistics are strange. Some repeaters produce bursts in dense clusters, dozens of bursts in a few hours, then silence for weeks or months. Others produce sporadic bursts with no obvious pattern. The waiting times between bursts follow power law distributions in some sources and exponential distributions in others. Different repeaters seem to be doing different things. And what about the apparently one-time bursts? The sources that have been seen to produce a single flash and then never again, despite years of follow-up observation. If magnetars are responsible for all fast radio bursts, why would some magnetars burst once and fall silent while others burst hundreds of times? Is it something about the age of the magnetar, the strength of the field, the environment around the star, or are the one-time bursts simply repeaters with very long intervals, sources that will burst again in a decade or a century, patient beyond our ability to wait? Rest with that uncertainty for a moment. Let it settle into the texture of everything we have discussed. This is not a story with a clean conclusion. This is a story about the edge of knowledge, where the answers are still forming, where every detection refines the questions rather than closing them. Now let us turn our attention outward, away from the neutron star itself and toward the environment in which it lives. A magnetar does not exist in isolation. It is embedded in the aftermath of the supernova that created it, an expanding shell of debris glowing with the heat of the explosion, threaded with magnetic fields and shock waves and hot plasma. This supernova remnant can persist for tens of thousands of years, slowly expanding and cooling, mixing with the surrounding interstellar medium. For a young magnetar, this remnant is home. Some fast radio bursts show signs of propagation through dense magnetized environments. The bursts arrive slightly later at lower frequencies. This is the dispersion measure we discussed, caused by passage through ionized plasma. But some bursts also show rotation measure, a signature of passage through magnetized plasma that rotates the polarization angle of the radio waves. High rotation measures suggest dense, strongly magnetized environments close to the source. The repeating source, FRB 2012-102A, has an enormous rotation measure, among the highest ever observed for any astrophysical source. This tells us that the radio waves are passing through an extremely magnetized, dense environment on their way to us. One possibility is a surrounding nebula, perhaps the remains of a supernova, or a wind of particles blown off the magnetar itself over millions of years. Another possibility is that the magnetar is embedded in an unusual environment, perhaps near the central black hole of its host galaxy, where magnetic fields and plasma densities are extreme. The host galaxies of fast radio bursts provide additional clues. Most bursts that have been precisely localized come from relatively ordinary galaxies, not exceptional in any obvious way. But some, particularly the prolific repeaters, seem to prefer small, actively star-forming dwarf galaxies. These are galaxies in the process of building new stars, environments where massive stars are being born and dying, where supernovae are common, where young neutron stars and magnetars would be expected to exist. This makes sense if magnetars are the source. Young magnetars would be found in regions of recent star formation, in the debris fields of recent supernovae. The correlation with star-forming galaxies supports the magnetar hypothesis, but it is not perfect. Some fast radio bursts come from older stellar populations, from galaxies with little ongoing star formation. If all bursts come from magnetars, and magnetars are young objects, their extreme magnetic fields are thought to decay over tens of thousands of years, then what are these bursts doing in old, quiet galaxies? One possibility is that magnetars can form through other channels besides core collapse supernovae. The merger of two neutron stars, for example, can produce a single highly magnetized neutron star with a very strong magnetic field. These merger remnants might live in older stellar populations, in galaxies where the original star formation happened billions of years ago, but the neutron star binaries are only now completing their long, slow, gravitational spiral inward. Another possibility is that the field decay timescale is longer than we think, that magnetars can remain active for hundreds of thousands or even millions of years, giving them time to appear in older stellar environments. Or perhaps, and this is the possibility that keeps theorists humble, perhaps not all fast radio bursts come from magnetars. Perhaps there are multiple source populations, different physical mechanisms producing similar signals, a zoo of progenitors that we have not yet learned to distinguish. Let that possibility float in the darkness for a moment. The universe does not owe us simple answers. There is no cosmic rule that says all phenomena with similar observational signatures must have the same cause. Gamma-ray bursts, when they were first discovered, turned out to come from at least two distinct populations, short bursts from neutron star mergers and long bursts from the collapse of massive stars. Supernovae come in multiple types, with different progenitors and different mechanisms. It would not be surprising if fast radio bursts similarly split into families as our understanding deepens. Some theorists have proposed exotic alternatives to the magnetar model. Consider the possibility of collisions, not between neutron stars themselves, but between neutron stars and smaller objects. An asteroid falling onto a neutron star, for example, would release enormous energy as it is crushed and converted to radiation by the extreme gravity. Could this produce a fast radio burst? The timescale might be right, the energy budget might be achievable, but would it produce the coherent radio emission we observe? This is unclear. What about black holes? A small object falling into a black hole releases energy, but most of that energy falls through the event horizon and is lost to the external universe. It is difficult to see how this could produce the observed bursts, but some models involve material orbiting close to a black hole, or interactions between a black hole and a surrounding magnetized disk. These are speculative, but they cannot yet be ruled out. And then there are the truly exotic possibilities, the ideas that live at the border between physics and science fiction. Cosmic strings, for example. These are hypothetical defects in space-time left over from the very early universe, infinitely thin lines of concentrated energy stretching across cosmic distances. If cosmic strings exist, and if they intersect or oscillate in certain ways, they might produce bursts of electromagnetic radiation. The predictions are uncertain, the physics is speculative, and no cosmic strings have ever been directly observed. But the fast radio burst community has looked for signatures that might distinguish a cosmic string origin from more conventional astrophysical sources. So far, no clear evidence has emerged, but the search continues. In science, you do not stop looking for alternatives just because you have a leading hypothesis. You test the hypothesis against every alternative you can imagine, and you remain alert to observations that might surprise you. The honest answer, as of today, is that we have strong circumstantial evidence pointing toward magnetars as the primary source of fast radio bursts. The 2020 galactic detection was a powerful confirmation of this connection. The environments, the timescales, the energy budgets, all of it fits reasonably well. But we cannot yet explain every observation. We cannot explain why some sources repeat prolifically, while others seem silent after a single burst. We cannot fully account for the range of luminosities, the diversity of host galaxy environments, the strange periodicities seen in some repeating sources. We cannot definitively rule out the possibility that multiple physical mechanisms contribute to the observed population. The magnetar hypothesis is the best answer we have, but it is not yet the final answer, and perhaps that is appropriate. Perhaps the universe has not finished teaching us what fast radio bursts are. Perhaps the thousands of detections we have accumulated so far are just the beginning, the first chapter of a story that will continue to unfold as telescopes improve and new instruments come online and patient astronomers continue their watch. The signals keep arriving. A few times a day, somewhere on Earth, a radio telescope records another flash, another millisecond-long eruption of energy from the distant cosmos. Each one carries information about its source and about every cubic centimetre of space it traversed on its billion-year journey to us. Each one is a puzzle piece, waiting to be fitted into a picture we have not yet fully assembled. In the silence between bursts, the magnetars spin on. The crustal stresses build. The magnetic fields store their energy in invisible configurations, waiting for the moment of release. Somewhere, right now, in a galaxy too far for us to ever visit, a neutron star is preparing to crack. A starquake is forming. A burst is about to be born. We will not detect it for millions or billions of years, depending on the distance. The light, the radio waves, are only beginning their long journey through the intergalactic medium, through plasma and magnetic fields and the expanding void between clusters of galaxies. They will arrive someday, a faint whisper from a cosmic catastrophe that happened before our sun was born, before Earth existed, before the atoms in your body were assembled from the debris of ancient supernovae. And when they arrive, we will be listening. The listening itself is a story worth telling, because there is a profound difference between a signal arriving and a signal being heard. For most of human history, fast radio bursts were washing over our planet continuously, multiple times per hour, and we had no idea. The universe was shouting, and we were deaf to the frequency. The radio dishes that finally opened our ears to these signals are themselves monuments to human patience and ingenuity, and they have their own personalities, their own strengths and weaknesses, their own ways of watching the sky. Consider the Parkes radio telescope in Australia, the instrument that detected the first fast radio burst in 2007, though that detection was not recognised until years later, buried in archival data that a graduate student was sifting through for a different purpose entirely. Parkes is a single dish, 64 metres in diameter, nestled in the sheep farming country of New South Wales. It has been operating since 1961. It tracked the Apollo 11 lunar module as Neil Armstrong stepped onto the moon. It discovered the first pulsar outside our own galaxy, and for decades it recorded radio signals from the cosmos, without anyone realising that some of those signals were fast radio bursts. The dish at Parkes moves on a massive mechanical mount, pointing at one small patch of sky at a time. This is both its strength and its limitation. It can stare at a single target with exquisite sensitivity, collecting faint signals that broader surveys might miss. But it sees only where it is pointed. A fast radio burst arriving from a different direction will go unrecorded. For an event that lasts only milliseconds, this is a significant constraint. You cannot predict where the next burst will come from. You can only point your telescope at a particular piece of sky and hope that something happens to flash while you are watching. This is why the discovery of fast radio bursts was so slow to unfold. The first detection at Parkes was a single event, a single data point, with no follow-up observations because no one knew what they were looking for. It took years of additional searching, additional analysis, and the involvement of other observatories before the astronomical community became convinced that fast radio bursts were a genuine cosmic phenomenon, and not some form of terrestrial interference or instrumental artifact. The turning point came with repetition. In 2016, a burst source was found that repeated FRB 12 London 2, the first repeater. This source did not flash once and fall silent. It flashed again, and again, and again. Over the following months and years, astronomers recorded hundreds of bursts from this single location in the sky. The repetition proved, beyond any reasonable doubt, that at least some fast radio bursts came from sources that survived the emission process. Whatever was producing these signals was not destroying itself. It was reloading, recharging, firing again. The discovery of the first repeater transformed the field. Suddenly you could point a telescope at a known burst location and wait for more signals to arrive. You could study the same source over time, watch how its bursts evolved, measure the intervals between emissions, look for patterns, and you could localize the source with far greater precision than a single fleeting detection would allow. Localization is the key that unlocks everything else. A burst that lasts only a few milliseconds, detected by a single radio dish, cannot be traced to a specific galaxy. The sky is simply too large, and the positional uncertainty of a single dish detection is simply too great. You know roughly which direction the signal came from, but roughly is not good enough. The error region might contain thousands of galaxies, each one a potential host. Without knowing which galaxy produced the burst, you cannot measure its distance accurately. You cannot determine its true energy output. You cannot study its local environment. You are left with a signal and a mystery, but no address to send your follow-up observations. The solution is interferometry, the technique of combining signals from multiple widely separated radio telescopes to create a single instrument with the angular resolution of a dish far larger than any that could actually be built. When the same radio wave arrives at telescopes separated by hundreds or thousands of kilometers, the tiny differences in arrival time can be measured with extraordinary precision. These timing differences encode information about the direction the wave came from. By combining data from multiple telescopes in multiple locations, astronomers can pinpoint the origin of a radio signal to within a fraction of an arcsecond, a tiny sliver of sky, small enough to identify a single galaxy, sometimes even a single region within that galaxy. This is how FRB 12112 was finally localized to its host galaxy, a small irregular dwarf galaxy about 3 billion light-years away. The process took years of patient observation and coordination among radio telescope networks spanning multiple continents. The Very Large Array in New Mexico played a crucial role, as did the European VLBI network, a collection of radio dishes scattered across Europe and beyond that worked together as a single enormous instrument. When all the data was combined, the position of the repeating source was known to better than 1,000th of an arcsecond, precise enough to place it in a specific star-forming region within its host galaxy. The discovery of that host galaxy was startling. It was not the kind of galaxy astronomers had expected. The theories at the time favoured older, more settled environments, elliptical galaxies perhaps, where neutron stars had been quietly spinning down for billions of years. Instead, FRB 12112 resided in a small, irregular, actively star-forming dwarf galaxy, the kind of chaotic environment where massive stars live fast and die young. This suggested a young magniator, recently born from a massive star's death, still in the process of releasing its magnetic energy through violent outbursts. The host galaxy finding was a piece of the puzzle that fit the magnetar hypothesis, though it raised questions of its own. But the real revolution in our ability to detect and study fast radio bursts came with the construction of a new kind of instrument, a radio telescope designed from the beginning to find these fleeting signals. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, was originally built to study the large-scale structure of the universe by mapping the distribution of hydrogen gas at different cosmic epochs. Its design was unusual. Instead of a single pointing dish, CHIME consists of 4 enormous cylindrical reflectors, each one 100 meters long and 20 meters wide, oriented along a north-south axis and fixed in place, unable to move. The reflectors focus incoming radio waves onto a line of receivers, and sophisticated digital processing combines the signals to create a radio image of a strip of sky passing overhead as the Earth rotates. The result is an instrument that sees about 200 square degrees of sky at any given moment, a field of view thousands of times larger than a traditional radio dish. And because the Earth rotates, CHIME's field of view sweeps across the entire northern sky every day. CHIME does not point at specific targets. It watches everything, all the time, waiting for something to flash. For fast radio burst science, this is transformative. The limiting factor had always been sky coverage. A traditional dish might spend months pointed at a known burst source, waiting for it to repeat, while missing hundreds of new bursts happening elsewhere. CHIME changed the equation. It began science operations in 2018, and within its first year it had detected more fast radio bursts than had been found in the entire previous decade. The catalogue exploded. Thousands of bursts poured in, each one a new data point, a new puzzle piece, a new thread to pull. CHIME revealed patterns that had been invisible when only a handful of bursts were known. It found repeating sources and apparently non-repeating sources in proportions that began to constrain theoretical models. It measured dispersion measures across a wide range of distances, using the bursts as probes of the ionized gas along their paths. It detected bursts from nearby galaxies and from the depths of the cosmic web. And it did all of this with a design that cost a small fraction of what traditional radio telescopes require. A testament to the power of clever engineering and digital signal processing over brute force construction. But CHIME has limitations of its own. Because it is a fixed instrument, it cannot follow up its own detections immediately. When CHIME sees a burst, it records the data and reports the discovery, but it cannot slew to examine the source more closely. That task falls to other observatories, which must be coordinated rapidly to catch any afterglow or follow-up emission before it fades. And while CHIME's positional accuracy is good enough to narrow down the source to a small region of sky, it is not as precise as the very long baseline interferometry networks that can pinpoint a burst to within a single galaxy. For the finest localization, you still need multiple dishes working together across continental scales. The next generation of radio instruments will push these capabilities even further. The Square Kilometre Array, or SKA, is under construction across sites in South Africa and Australia. When completed, it will be the most sensitive radio telescope ever built, with a collecting area approaching a square kilometre, 1 million square metres of radio wave gathering surface distributed across thousands of individual antennas. The SEA will be able to detect fast radio bursts at greater distances than any current instrument, and it will localise them with unprecedented precision. It will find bursts so faint that they are invisible to current telescopes, probing populations that we can currently only theorise about. And it will do this automatically, scanning the sky with software systems designed to identify and characterise bursts in real time. The sensitivity of the SKA matters because the fast radio burst population almost certainly extends to far greater distances than we can currently observe. The bursts we detect today are the luminous ones, the cosmic shouts that carry across billions of light years and still arrive with enough energy to register on our instruments. But for every shout, there may be thousands of whispers, fainter bursts, more distant bursts, bursts from sources that are intrinsically less powerful or farther away. The known population is biased toward the brightest events, because those are the ones we can see. The true population may be far larger and more diverse. This is the observer's eternal dilemma. You can only study what you can detect. Everything else remains invisible, unknown, potentially crucial to understanding the phenomenon but inaccessible until your instruments improve. The history of astronomy is littered with examples of populations that seemed simple until better telescopes revealed unexpected complexity. The fast radio burst population may be the same. The magnetar hypothesis explains the bright nearby events we have studied in detail. But what about the faint events we cannot see? What about the distant sources at the edge of detectability? What about the bursts that fall below the threshold of our current instruments? There is another axis of observation that deserves attention. Time. Not the millisecond timescale of the bursts themselves, but the longer timescales over which burst activity evolves. Some sources repeat frequently, producing dozens or hundreds of bursts over weeks or months. Others seem to fall silent after a single detection, never flashing again despite years of follow-up observation. Still others show strange periodicities, bursting in predictable windows and then going quiet for extended periods. FRB 18091 is perhaps the most famous example of periodic behaviour. This repeating source follows a 16-day cycle, approximately 4 days during which bursts may occur, followed by approximately 12 days of silence, then another 4-day window, then silence, repeating with remarkable regularity. The period has been stable over multiple years of observation. Something about this source, its rotation, its orbit, the precession of a beam, operates on a 16-day clock. The interpretation of this periodicity is not settled. One possibility is that the source is part of a binary system, a magnetar orbiting a companion star or a black hole. The 16-day period might be the orbital period, and the bursting window might correspond to the portion of the orbit when the line of sight to Earth passes through a region favourable for emission. Another possibility involves precession, the slow wobble of the magnetar's rotation axis, which would cause its emission beam to sweep across different directions over time. A third possibility involves the companion itself. If the magnetar is orbiting within the wind of a massive star, the density of material surrounding it might vary over the orbit, affecting whether the radio waves can escape or are absorbed. Each explanation carries implications. A binary origin would mean that at least some fast radio bursts come from magnetars in specific environments, influenced by the presence of nearby companions. A precession origin would tell us something about the internal structure of the neutron star, the relationship between its crust and its core. A wind absorption origin would connect the burst activity to the evolutionary state of the companion star, which itself provides clues about the magnetar's age and formation history. But the 16-day periodicity of FRB 180916 is not the only temporal pattern astronomers have detected. Some repeating sources show clustering of their bursts, episodes of intense activity followed by long quiescent periods with no obvious regularity. Others show hints of shorter periodicities nested within longer cycles. The data is noisy, the statistics are limited, and distinguishing genuine periodicity from chance clustering is a delicate business. But the search for temporal structure continues, because any real pattern would be a window into the physics of the source. Consider the implications of weighting. If you point a telescope at a known repeater and it fails to burst during your observation window, what have you learned? Perhaps the source is genuinely quiet at the moment. Perhaps you missed an active window by hours or days. Perhaps the source is entering a longer quiescent phase, one that might last weeks or months or years. The absence of a burst is information, but it is difficult information to interpret. The patience required to study these sources is measured in months and years. After KIME detects a new burst, astronomers must decide whether to devote precious telescope time to following it up. If the burst does not repeat, that time may be spent staring at empty sky, waiting for a signal that never comes. If it does repeat, you might catch another flash, another data point, another piece of the puzzle. The decisions are probabilistic, the outcomes uncertain, and the observers keep watching, because there is no other way to learn. There is something meditative about this kind of science. The universe does not reveal its secrets on a human schedule. You cannot command a magnetar to burst. You cannot accelerate the journey of radio waves across billions of light years. You can only build your instruments, point them at the sky, and wait. The waiting is part of the work. The patience is part of the method. And every now and then the universe rewards the patient observer with a flash of light that no one predicted, a signal that changes everything. The instruments themselves are evolving, learning to watch in new ways. Real-time detection systems are becoming more sophisticated, able to identify bursts as they arrive and trigger immediate follow-up observations at other wavelengths. When a radio burst is detected, alerts can be sent to optical and X-ray telescopes within seconds, allowing them to search for any accompanying emission that might reveal more about the source. Most of the time, these rapid follow-ups find nothing. The bursts seem to be pure radio events, at least for the vast majority of cases, but the search continues because a single detection of an optical or X-ray counterpart would be enormously valuable. The exception, once again, is the galactic burst of April 2020. When SGR 1935+2-154 flared, X-ray satellites detected the simultaneous high-energy emission that accompanied the radio burst. This multi-wavelength detection confirmed that fast radio bursts and X-ray flares from magnetars are related phenomena, different facets of the same underlying physics. But the galactic magnetar is close, comparatively speaking, a mere 30,000 light-years away, within our own Milky Way. Detecting similar X-ray emission from an extragalactic burst, millions or billions of light-years distant, would require extraordinary luck or extraordinary sensitivity or both. The geometry matters. If the X-ray emission from a magnetar flare is beamed in a different direction than the radio emission, We might see the radio without seeing the X-rays, even if both are produced simultaneously. The universe could be full of fast radio bursts accompanied by X-ray flares that we will never detect because the X-rays are simply not pointed at us. This is a fundamental limitation of observational astronomy. We see only what is aimed our way. Everything else remains inference. And so, the watch continues. The radio telescopes scan the sky, their receivers humming with the faint noise of the cosmos. The software systems process the data in real time, searching for the characteristic sweep of dispersion that marks a signal from beyond our galaxy. The astronomers monitor their alerts, ready to coordinate follow-up observations when something interesting arrives. And somewhere out there in galaxies we have never named, magnetars continue their slow decay, their magnetic fields tangled into knots of unimaginable energy, their crusts straining under forces that will eventually demand release. The next burst is always coming. The question is never whether another signal will arrive, but when and from where and what it will teach us. The universe is profligate with these signals, scattering them across the cosmos like seeds on the wind. We catch only a tiny fraction. The rest pass through our atmosphere, through our instruments, through our bodies, and vanish into the vast empty spaces beyond, never to be detected by anything. But the fraction we do catch is enough. It is enough to tell us that the universe is stranger than we imagined. It is enough to confirm that neutron stars really do behave in the extraordinary ways that theory predicted. It is enough to provide us with a new tool for measuring the cosmos, a new probe of the matter and energy that fills the void between galaxies. And it is enough to remind us that there is always more to learn, always another mystery waiting just beyond the edge of our current understanding. The signals keep arriving, the instruments keep listening, and slowly, patiently, the picture comes into focus. The picture that emerges is not a photograph. It is more like a mosaic assembled from fragments, each piece placed carefully beside the others, the full image visible only when you step back far enough to see the pattern. And one of the strangest pieces of that mosaic is this. Fast radio bursts are not all the same brightness. They span an enormous range of energies, from relatively modest flashes to eruptions of almost incomprehensible power. The faintest bursts we detect release the energy equivalent of our sun's entire output over a few days, compressed into a few milliseconds. The brightest bursts release the energy equivalent of our sun's output over thousands of years, again compressed into that same impossible sliver of time. This range, or this dynamic range as astronomers call it, is itself a clue. It tells us that whatever produces these bursts can operate across a vast spectrum of intensities. A magnetar might release a modest flare one day, and a catastrophic eruption the next. The mechanism is the same, but the scale varies wildly. Think of it this way. Imagine a geyser that sometimes produces a gentle plume of steam, and sometimes produces an explosion that could be seen from space. The underlying physics is identical, water heated by volcanic energy, pressure building until release becomes inevitable. But the amount of energy involved can differ by factors of millions. Magnetars appear to work similarly. The magnetic reconnection events that power their bursts can be small and local, affecting only a patch of the neutron star's surface, or they can be global catastrophes that involve the entire stellar crust. The largest events might even be triggered by starquakes, sudden shifts in the neutron star's structure as it settles into new configurations under the crushing weight of its own gravity. A neutron star is not solid in the way a rock is solid. Its outer crust is a crystalline lattice of iron nuclei, held in place by the immense pressure of the layers above. But below the crust, matter becomes stranger. The nuclei begin to merge, neutrons drip free of their nuclear prisons, and eventually, deep in the core, matter may take on forms that physicists can only speculate about. Some models suggest that the core contains a sea of free quarks, the fundamental particles that normally exist only bound together inside protons and neutrons. Others suggest exotic forms of matter that have never been observed in any laboratory on Earth. We do not know what lies at the heart of a neutron star. The pressures are too extreme, the densities too high, the conditions too far removed from anything we can recreate. But we know that whatever exists down there, it is under constant strain. A neutron star is a battleground between gravity, which wants to crush everything into a point, and quantum pressure, which resists that collapse. The balance is precarious, and when the balance shifts even slightly, the entire star can shudder. A starquake on a neutron star is nothing like an earthquake on Earth. The energy involved is billions of times greater. The crust can crack and shift, and when it does, the magnetic field lines anchored to that crust are suddenly displaced. This displacement sends waves of energy rippling outward through the magnetosphere, the region of twisted magnetic fields surrounding the star. Some of that energy is converted into X-rays and gamma rays. Some of it apparently is converted into radio waves. The burst we detect on Earth, billions of years later, is the echo of a starquake that happened in a galaxy we will never visit, on a star we will never see, in conditions we can barely imagine. Let that settle for a moment. The flash of radio energy that sweeps through crimes receivers, that triggers alerts on astronomers' phones, that adds another point to the growing catalogue. That flash began as the shattering of a crystalline crust on an object smaller than a city, an object so dense that a teaspoon of its material would weigh as much as a mountain. The connection between cause and effect spans distances that light itself takes billions of years to cross. And yet, the signal arrives intact, carrying information about its origins, readable by anyone with the right instrument and the patience to listen. This is what radio astronomy has become, not just a way of seeing distant objects, but a way of feeling distant events. The bursts are tactile in a sense that ordinary starlight is not. When you detect a fast radio burst, you're not observing a steady glow that persists for millions of years. You're catching the moment of release, the instant of rupture, the heartbeat of a dead star having a seizure. The intimacy of that connection is easy to miss, but it is real. You are present, in a meaningful sense, for something happening in another galaxy. The light cone of the event has expanded far enough to include you. You were always going to be there for this burst, from the moment it was emitted, because the geometry of space-time guaranteed it. The burst was always going to reach Earth at this precise moment, and you were always going to be the generation of astronomers with the instruments capable of detecting it. The coincidence feels profound because it is profound. This is the universe, including you in its unfolding. But the magnetar model, compelling as it is, does not explain everything. There are bursts that do not fit neatly into the pattern. There are energies that seem too high, repetition rates that seem too fast, behaviours that seem too strange even for objects as extreme as magnetars. And there is one category of burst that continues to puzzle theorists, a category that may or may not exist depending on how you interpret the data. These are the bursts that appear to come from very old, very quiet galaxies, galaxies where star formation ceased billions of years ago, where no young massive stars remain to explode into supernovae, where no magnetars should exist at all. Magnetars are young objects. They are born in the deaths of massive stars, and they burn through their magnetic energy relatively quickly by cosmic standards. A magnetar's active phase, the period when its magnetic field is strong enough to power dramatic flares and bursts, lasts perhaps 10,000 years, maybe 100,000 at the outside. After that, the magnetic field has decayed too much, the star has cooled too far, and the object settles into quiet retirement as an ordinary pulsar or simply goes dark. In a galaxy where no stars have formed for billions of years, there should be no magnetars. The last massive stars would have exploded long ago, the last magnetars would have faded into silence, and the galaxy should be radio quiet in this particular way. And yet a handful of fast radio bursts appear to have been localized to exactly these kinds of galaxies. Old, red, dead galaxies, populated only by ancient stars that burn slowly and steadily, with no explosions, no catastrophes, no drama. If the localization is correct, these bursts cannot come from magnetars. They must come from something else. What could that something else be? The honest answer is that no one knows. But there are possibilities, and theorists have not been shy about proposing them. One possibility is that the localization is simply wrong. Pinpointing the location of a fast radio burst is difficult, and the error bars can be substantial. Perhaps the burst that appears to come from an old galaxy actually originated from a younger galaxy along the same line of sight, hidden behind or beside the apparent host. This is not an elegant solution, but it is a possible one. The universe is full of galaxies, and occasionally two of them will line up in a way that confuses our measurements. Another possibility is that magnetars can form in old galaxies through mechanisms that do not require recent star formation. Binary star systems, for example, can produce unusual stellar remnants. If two white dwarfs merge, the result can be a rapidly spinning, highly magnetized neutron star. Essentially, a magnetar born from objects that are themselves ancient. These merger-formed magnetars would be rare, but they would exist even in galaxies where normal star formation ceased eons ago. The timescales are different, the formation pathway is different, but the end result might be the same, an object capable of producing fast radio bursts. A third possibility is more exotic. Perhaps there are phenomena other than magnetars that can produce fast radio bursts. Perhaps the burst mechanism is not unique to highly magnetized neutron stars. Perhaps black holes, under certain circumstances, can produce similar signals. Perhaps collisions or interactions between neutron stars, even without merging, can release brief flashes of coherent radio emission. Perhaps there are objects in the universe that we have not yet discovered, objects that inhabit the old and quiet galaxies precisely because they are old and quiet, objects that reveal themselves only through these mysterious milliseconds of radio light. This uncertainty is not a weakness of the science, it is the science. Every good mystery contains elements that do not fit, details that resist explanation, clues that point in contradictory directions. If fast radio bursts were entirely explained by magnetars, if every observation confirmed the theory perfectly, if no puzzles remained, then the field would be essentially complete. Astronomers would move on to other questions, but the puzzles remain. The bursts from old galaxies remain unexplained. The extreme energies of some repeaters remain difficult to model. The fine structure of the bursts, the microbursts within bursts, the complex frequency behavior that some signals display. All of these details resist simple explanation. And this is why the field remains so active. This is why new telescopes are being built, new detection algorithms are being developed, new theories are being proposed and tested and revised. The mystery is alive. Every new detection adds a data point. Every localization narrows the possibilities. Every spectrum, every polarization measurement, every timing analysis brings us incrementally closer to understanding. The picture in the mosaic grows clearer, but it is not yet complete. Large sections remain blank, waiting for the pieces that will eventually fill them. Consider the question of environment. Where exactly within a galaxy do fast radio bursts originate? The answer varies, and the variation is meaningful. Some bursts come from the spiral arms of galaxies, the regions where new stars are actively forming, where massive stars live and die quickly, where you would expect to find young magnetars. This is consistent with the standard model. But other bursts come from the outskirts of their host galaxies, far from the regions of active star formation, and still others come from globular clusters, those ancient spherical collections of old stars that orbit the halos of galaxies. Globular clusters are among the oldest structures in the universe. Their stars formed more than 10 billion years ago, in the early epochs of cosmic history. Finding a fast radio burst in a globular cluster is like finding a fresh footprint in an ancient ruin. Something unexpected is happening. One explanation for globular cluster bursts is, again, binary evolution. Globular clusters are dense environments, packed with stars that frequently interact with each other. Binary systems form and evolve differently in these crowded conditions. Neutron stars can be recycled, spun up by material transferred from companion stars, rejuvenated in ways that would not happen in more isolated environments. Perhaps these recycled neutron stars, given the right conditions, can develop strong enough magnetic fields to produce bursts, even though they are themselves ancient. The physics is not fully understood, but it is not impossible. Another explanation involves more exotic objects. Globular clusters are thought to harbour populations of stellar mass black holes, left behind by the deaths of the cluster's most massive original stars. These black holes interact with each other and with neutron stars in complex ways. Perhaps some fast radio bursts are produced not by magnetars at all, but by the interactions between black holes and neutron stars, or between pairs of neutron stars, or by isolated black holes accreting material from their surroundings. The theoretical landscape is wide and varied, and the data are not yet sufficient to rule out many possibilities. What we can say is this: the universe uses many different pathways to produce these signals. Or perhaps it uses only one pathway, but that pathway can be reached through many different routes. A magnetar formed from a supernova and a magnetar formed from a white dwarf merger might behave identically once they exist. The burst-producing mechanism might be universal, even if the objects that host it have diverse origins. This is a common pattern in astrophysics. Black holes, for example, can form from the collapse of massive stars, from the merger of neutron stars, from the direct collapse of gas clouds in the early universe, or from the growth of smaller black holes over cosmic time. Once formed, a black hole is a black hole. Its past is erased. Only its mass, spin, and charge remain as identifying characteristics. Perhaps magnetars are similar. Perhaps the only thing that matters for producing a fast radio burst is the strength and configuration of the magnetic field, not the history of how that field came to be. Let me try to put this in perspective. You live on a planet orbiting an ordinary star in an ordinary galaxy. Around you, in every direction, space extends outward to distances that language struggles to convey. And scattered throughout that space, in galaxies young and old, in spiral arms and globular clusters, in the dense cores of starbursts and the quiet outskirts of ellipticals, neutron stars are releasing flashes of radio energy. Some of these neutron stars are young, only a few thousand years removed from the supernova that created them. Others may be ancient, recycled and rejuvenated through cosmic processes we're only beginning to understand. All of them are dead stars, remnants of nuclear furnaces that burned out long ago. And yet they are not inert. They continue to act upon the universe, to release energy, to send signals that cross the cosmos at the speed of light. The signals we detect are tiny. By the time a fast radio burst reaches Earth, the energy intercepted by even the largest radio telescope is almost too small to measure. We are talking about femtojoules, quadrillionths of a joule, amounts of energy that would not warm a single grain of sand by a perceptible amount, and yet that femtojoule of energy carries information. It carries the signature of its origins, encoded in its frequency structure, its polarization, its arrival time. It carries the imprint of everything it passed through on its journey: the plasma surrounding the source, the interstellar medium of the host galaxy, the intergalactic void, and finally our own Milky Way. It is a message in a bottle thrown into the cosmic ocean billions of years ago, arriving at our shores now, today, this moment. We cannot send a reply. The sources are too far, the journey too long, the signals one way only. But we can listen. We can build ever more sensitive instruments. We can develop ever more sophisticated algorithms. We can coordinate telescopes around the globe and beyond, creating networks that watch the sky continuously, that never blink, that catch every burst bright enough to detect. And we can learn. Every signal teaches us something. Every detection adds to our understanding. The magnetar hypothesis explains most of what we see. Highly magnetized neutron stars releasing pent-up magnetic energy through dramatic reconnection events, producing coherent radio emission through processes that we are still working to understand completely. This is the leading model, the framework within which most astronomers interpret the data. But the model is not complete. The details are uncertain, the outliers remain unexplained, and the possibility exists, as it always does in science, that we are missing something fundamental, that some piece of the puzzle is still hidden, waiting to be discovered. Perhaps the magnetars are just one class of source among several. Perhaps fast radio bursts are produced by multiple types of objects, each leaving its own subtle signature in the data, the signatures blending together into a population that appears more homogeneous than it actually is. Or perhaps the magnetar model is correct but incomplete, lacking some crucial piece of physics that would explain the most extreme events, the most rapid repetitions, the most unusual host environments. The data will eventually tell us which possibility is true. The signals will continue to arrive, each one carrying its tiny cargo of information, each one nudging the mosaic one step closer to completion. And this brings us to a question that astronomers rarely ask aloud, but that hovers in the background of every discussion about fast radio bursts, every conference presentation, every late-night speculation session. What if we are missing the most important signals entirely? What if the bursts we detect are only the tip of an iceberg, the visible minority of a much larger population that remains forever hidden? This is not paranoia. It is a serious consideration rooted in the physics of detection. Our telescopes have sensitivity limits. A burst that is too faint or too far away or too brief will simply not register above the noise floor. We know this. We account for it in our population models, extrapolating from the detected bursts to estimate how many undetected bursts must be occurring throughout the universe. The numbers are staggering. Current estimates suggest that fast radio bursts occur somewhere in the universe roughly 10,000 times per day. That is one burst every few seconds, somewhere in the observable cosmos. We detect a tiny fraction of these, perhaps a few thousand bursts per year, with the most sensitive current instruments. The rest are lost, either because they are too faint, or because they occur in parts of the sky we're not watching, or because our instruments are momentarily occupied with other observations. But sensitivity limits are not the only concern. There is also the question of bandwidth. Our radio telescopes observe within specific frequency ranges. CHIME operates between 400 and 800 MHz. Parkes typically observes at 1.4 GHz. Other instruments observe at other frequencies. But what if some fast radio bursts are emitted at frequencies we're not monitoring? What if there are bursts at very low frequencies, below 100 MHz, where Earth's ionosphere makes observations difficult? What if there are bursts at very high frequencies, above 10 GHz, where different types of telescopes are needed? We could be missing entire populations of bursts simply because we are not listening in the right part of the electromagnetic spectrum. The universe does not arrange itself for our convenience. It does not label its signals or emit them only at the frequencies we happen to be monitoring. If we want to understand the full phenomenon of fast radio bursts, we need to expand our search to cover more frequencies, more of the sky, more of the time. This is exactly what astronomers are working to do. New instruments are coming online that will observe at low frequencies in the regime below 300 MHz. Others will push to higher frequencies. Still others will watch the sky continuously around the clock, ensuring that no significant burst escapes detection, simply because we were looking elsewhere when it arrived. The effort is global. It involves dozens of institutions, hundreds of researchers, millions of dollars of funding, and years of patient work. And it is motivated by a simple conviction: that fast radio bursts have more to teach us, that the mystery is not yet solved, that the best discoveries may still lie ahead. But there is another question, quieter and more unsettling, that surfaces when astronomers contemplate the limits of their instruments. It is a question about timing. Not the millisecond timing of the bursts themselves, but the cosmic timing of our presence here as observers. We exist at a particular moment in the history of the universe. We have been capable of detecting radio signals from space for less than a century. We have been capable of detecting fast radio bursts for less than 2 decades. And we will presumably continue improving our instruments, refining our techniques, expanding our reach into the electromagnetic spectrum. But we are still, by cosmic standards, newcomers to the practice of listening. Consider what this means. The universe has been generating radio emission for billions of years. The first stars, forming a few 100 million years after the Big Bang, would have produced radio waves as they flared and died. The first supernovae would have sent out radio pulses as their shock waves expanded into the surrounding gas. The first neutron stars would have begun their tireless spinning, some of them presumably producing coherent radio beams, some of them perhaps producing bursts. All of this happened before there was anyone to listen. The universe was filled with signals that arrived on no receivers, that illuminated no detectors, that carried information to no minds capable of interpreting it. And here is the humbling part. That silent broadcasting has been ongoing for approximately 13.8 billion years. Human radio astronomy has existed for roughly 90 years. The ratio between these two numbers is staggering. Imagine all the radio signals the universe has ever produced, drawn as a single line stretching from one side of a football field to the other. Human observation would occupy a length smaller than the width of a single blade of grass somewhere near the far end zone. We are latecomers to a conversation that has been ongoing since before our galaxy existed. This means that countless signals have already passed us by. Whatever bursts occurred in the distant past, whatever information they carried about the conditions of the early universe, whatever patterns they might have revealed about the birth of the first magnetic objects, all of it arrived at our location in space before we had the capacity to notice. The photons passed through the region that would eventually become Earth, continued on into the void, and will never return. Those signals are gone forever, scattered across an ever-expanding universe, diluted into unrecoverable noise. Let this thought settle for a moment. The archive of the universe's radio history is not stored anywhere. It exists only in the brief window during which the signals are actually passing through a given location. After that, the information disperses. We can observe what is happening now, We can observe what is arriving from various distances and therefore various times, but we cannot rewind the tape. We cannot access the signals that arrived before we began watching. The universe does not maintain a recording studio. It broadcasts once, and that broadcast either finds a listener or it doesn't. This might seem like a melancholy observation, a reminder of how much we have necessarily missed. And in one sense it is. But there is another way to see it, a perspective that transforms the loss into something closer to gratitude. Consider that we are here now, at a moment when fast radio bursts are detectable and still mysterious. We arrived at the practice of radio astronomy at precisely the right time to participate in this particular discovery. 100 years earlier, and we would have had no instruments capable of finding the Lorimer burst. 100 years later, and the mystery might already be solved, the phenomenon catalogued and filed away with pulsars and quasars and all the other once mysterious objects that have become routine. Instead, we exist at the hinge point. We are present for the unfolding. We can watch as the data accumulates, as the theories compete and merge and evolve, as the picture slowly clarifies into something we do not yet know. This is not a common experience in the history of science. Most discoveries are encountered after the fact in textbooks already explained. The opportunity to witness a fundamental discovery in progress, to see the confusion and the competing hypotheses and the gradual convergence toward understanding. This is a gift that comes rarely, and it will not last forever. The mystery will eventually be solved. It might take 5 years or 50, but someday a consensus will emerge, a model will be confirmed, and fast radio bursts will join the catalogue of understood phenomena. When that happens, the mystery will close, and the particular excitement of not knowing will fade into the satisfaction of comprehension. Both states have their value, but only one of them is available to us right now, and it will not wait forever. There is also the question of what else the universe might be signalling that we have not yet learned to hear. Fast radio bursts are defined by their particular characteristics: millisecond duration, radio frequencies, cosmological distances, enormous implied energies. But these characteristics are somewhat arbitrary boundaries drawn by our current instruments and our current understanding. The universe does not categorize its phenomena according to human definitions. It simply produces what it produces, and we discover what our tools allow us to detect. What other categories of signal might exist that we have not yet defined, because we have not yet found examples? What transient events might occur at frequencies we are not monitoring, with durations we are not equipped to resolve, with characteristics that fall outside the parameter space we have thought to explore? The history of astronomy is filled with objects that were discovered because someone looked in a new way, at a new wavelength, with a new technique, at a new time scale. Every expansion of our observational capacity has revealed phenomena that were previously invisible. There is no reason to think this process has ended. Fast radio bursts themselves are an example of this pattern. Before the Lorimer burst, astronomers were not systematically searching for millisecond duration extragalactic radio pulses. The parameter space existed, but no one was exploring it with sufficient sensitivity and time resolution. When Duncan Lorimer looked at that archival data from 2001, he was doing something new, applying a search technique at a timescale that had not been thoroughly examined. And he found something. The universe had been producing these signals all along, but we only noticed when we developed the right combination of instrument and method and attention. Now extrapolate this lesson forward. What parameter spaces remain unexplored? What combinations of frequency, duration, arrival time, and sky position have we not yet examined with sufficient care? The honest answer is that we do not know, because by definition we cannot know what we have not yet looked for. But the implication is clear. The catalogue of known phenomena is almost certainly incomplete. The universe is almost certainly doing things we have not yet noticed, producing signals we have not yet detected, following processes we have not yet imagined. This is both daunting and exhilarating. Daunting because it reminds us how partial our picture remains, how much the darkness conceals. Exhilarating because it promises that the age of discovery is not over, that there are still fundamental surprises waiting in the data, that the next Lorimer burst, the next utterly unexpected signal that upends our assumptions, could arrive at any moment. Let us return then to the burst we know. The thousands of detected signals, the growing catalogue, the emerging patterns, the persistent puzzles. What do they tell us about the universe we inhabit? What do they reveal about the conditions in distant galaxies, the populations of extreme objects, the physics of matter under impossible strain? The answer is that they tell us a great deal, but always through a glass darkly, always filtered through inference and modelling and the limitations of our instruments. Consider what each detection actually represents. A burst arrives at Earth after travelling billions of years across expanding space. It has been stretched by that expansion, reddened, weakened. It has passed through multiple galaxies worth of intervening material, accumulating dispersion along the way. It arrives at our telescopes carrying information about all of those interactions embedded in its structure. The dispersion measure tells us about the total column of electrons along the path. The scattering tells us about turbulence in the intervening medium. The polarization tells us about magnetic fields. The spectrum tells us about the emission mechanism and any absorption along the way. Each burst is therefore a probe, a needle threaded through billions of light years of cosmic material, sampling the conditions all along its path. This is why astronomers are so eager to localize bursts to their host galaxies. When we know where a burst comes from, we can calculate how much dispersion should be contributed by the Milky Way, how much by the host galaxy, and how much by the intergalactic medium between them. That intergalactic contribution is precious. It tells us about the material that fills the vast voids between galaxies, the baronic matter that standard models predict should exist, but that has been surprisingly difficult to detect by other means. For decades, astronomers have grappled with what is sometimes called the missing baryon problem. The Big Bang produced a specific amount of ordinary matter, protons, neutrons, electrons, the stuff that makes up stars and planets and people. We can calculate how much there should be. But when we add up all the matter we can see, in galaxies, in clusters, in hot gas between clusters, we come up short. Roughly half the baryons seem to be missing. They are not in galaxies. They are not in the obvious places. Where are they? The answer, most cosmologists believe, is that they are spread thinly through the intergalactic medium in a diffuse web of gas that connects galaxies across cosmic distances. This gas is too cool to emit X-rays, too sparse to produce much visible light, too spread out to detect by most conventional methods. But it is not invisible. It is made of atoms, which means it contains free electrons, which means it contributes to dispersion. Fast radio bursts can find these missing baryons. When a burst travels through the intergalactic web, every electron along its path adds to the dispersion measure. By comparing the total dispersion to the contributions from the Milky Way and the host galaxy, astronomers can isolate the intergalactic component, and by doing this for many bursts at many distances, they can map the density of the intergalactic medium, measuring exactly how much matter fills the voids between galaxies. This project is already underway. Early results are encouraging. The dispersion measures of localized bursts are consistent with the expected density of intergalactic electrons, which in turn is consistent with the missing baryons being distributed in the predicted cosmic web. It is not yet a complete accounting, not yet a definitive solution to the missing baryon problem, but it is progress. Fast radio bursts are serving as cosmic rulers, measuring the content of the universe along each line of sight, probing the spaces between galaxies where almost nothing else can reach. And this is only one application. The same bursts that measure baryons also measure the expansion rate of the universe. The relationship between a burst's redshift and its dispersion measure depends on how the universe has expanded over time. With enough bursts at enough distances, astronomers can use this relationship to constrain cosmological parameters, the Hubble constant, the density of dark energy, the geometry of space itself. Fast radio bursts are becoming cosmological tools, probing the structure of the universe at the larger scales. They are also becoming laboratories for fundamental physics. The signals that travel billions of light years before arriving at Earth are exquisitely sensitive to any effects that might accumulate over those vast distances. If the speed of light varies slightly with frequency, that variation would show up in the arrival times of different parts of the burst spectrum. If photons have even a tiny rest mass, that mass would cause lower frequency components to lag behind higher frequency ones. If Lorentz invariance, the principle that the laws of physics look the same to all observers regardless of their motion, is violated at some level, that violation might manifest in the behaviour of these signals. So far, fast radio bursts have been used to place some of the tightest constraints on photon mass and on certain types of Lorentz invariance violation. The limits are extraordinary. The photon mass, if it exists at all, must be so small that it has essentially no effect on the propagation of light across the universe. This is not surprising. Most physicists expect the photon to be exactly massless. But it is reassuring to have the experimental confirmation, and it demonstrates the power of these signals as probes of fundamental physics. Rest with that for a moment. A millisecond flash of radio light from a distant galaxy can tell us about the mass of the photon, the density of intergalactic space, the expansion rate of the universe, and the physics of neutron stars, all from a single detection. Each burst is not merely an astronomical curiosity, it is a multifaceted measurement, a data point that contributes to questions across multiple subfields. This is why the field has grown so rapidly, why so many researchers from so many backgrounds have converged on these signals. The bursts are useful, they are scientifically productive, they answer questions that have resisted other approaches. But usefulness is not the same as understanding. We can employ fast radio bursts as tools while still not knowing what creates them. The two projects, using the bursts and explaining the bursts, proceed in parallel, each informing the other. The better we understand the sources, the more confidently we can interpret what the signals tell us about the universe through which they travel. The more we learn about the universe from the signals, the better we can constrain the conditions in which the sources must operate. This interplay is characteristic of observational science. We rarely have the luxury of understanding one thing completely before moving on to the next. Instead, we work with partial knowledge, making progress on multiple fronts simultaneously, allowing each advance to illuminate the others. It can feel chaotic, especially from the outside. It can seem like astronomers are stumbling forward in the dark, making guesses, revising, occasionally tripping over unexpected obstacles. And in some sense they are. But the stumbling is productive. The guesses are informed by data. The revisions bring the picture into slowly sharper focus. That focus has sharpened considerably in the 17 years since Duncan Lorimer's discovery. We now know that fast radio bursts are real, that they are cosmological, that they originate in many different types of galaxies, that some of them repeat and some apparently do not, that at least some of them come from magnetars, that they are extraordinarily energetic, that they can be polarized and scattered and dispersed, that they arrive from every direction in the sky, and that they occur constantly throughout the observable universe. This is substantial progress. It represents the work of hundreds of researchers over thousands of observing hours, the deployment of new instruments, the development of new analysis techniques, the testing and rejection of many hypotheses. And yet the central question remains: what are they? The magnetar model is compelling for the repeaters, but it struggles with some of the one-off bursts. The catastrophic models are compelling for the one-offs, but they cannot explain repetition. The possibility that multiple source classes exist is increasingly accepted, but the details remain murky. We do not yet have a complete theory that explains all the observations, that predicts the full range of burst properties, that connects the emission mechanism to the underlying physics in a way that withstands scrutiny. This is the state of the mystery. We are somewhere in the middle of the story after the initial discovery and the early confusion, but before the final resolution. The data is accumulating, the instruments are improving, the theories are being tested and refined. The answer is out there, encoded in the signals themselves, waiting to be decoded by someone patient and clever enough to read it. Perhaps the next burst will carry the crucial clue. Perhaps it will come from a source so unusual, or will display properties so distinctive that the ambiguity will finally resolve. Or perhaps the answer will emerge gradually, not from any single detection, but from the statistical weight of thousands of bursts, each one contributing a small piece until the picture snaps into clarity. Either way, the signals keep arriving. Every few seconds, somewhere in the observable universe, a magnetar flares or a neutron star collides or some still unknown process ignites, sending another pulse of radio light outward into the cosmos. Most of these pulses will never be detected. They will pass through empty space, or arrive at frequencies we are not monitoring, or appear in regions of the sky where no telescope happens to be pointed. But some of them will find their way to our instruments. Some of them will register as blips of excess power in the data streams, triggering automated alerts, summoning astronomers to their screens to examine the latest arrival from the cosmic deep. Those arrivals are not slowing down. If anything, they are accelerating as new instruments come online, as old instruments are upgraded, as the global network of radio observatories expands its coverage. We are entering an era of fast radio burst abundance, when detections will number not in the hundreds per year but in the thousands, when the statistical power to distinguish between models will finally become overwhelming. The mystery that has persisted for nearly 2 decades may not persist for much longer, but until then, it remains open. The question hangs in the air, tantalizing and unresolved. Every burst that arrives carries with it the possibility of an answer, or the possibility of a deeper question, a new wrinkle, another layer of complexity that we had not anticipated. The universe is under no obligation to be simple, and it has shown a consistent tendency to be stranger than expected. Whatever the ultimate explanation for fast radio bursts turns out to be, it will probably contain surprises. It will probably reveal connections we had not imagined, physics we had not fully appreciated, conditions more extreme than we had contemplated, and this is perhaps the deepest truth about these signals. They are not just puzzles to be solved. They are windows into conditions that exist nowhere else in the observable universe, laboratories that no earthly facility could ever replicate, experiments that nature has been running for billions of years without our permission or participation. When a magnetar flares, it creates magnetic field strengths that exceed anything humanity has ever produced by factors of trillions. When neutron stars collide, they generate gravitational waves and electromagnetic radiation in a synchronized burst that reveals the fundamental nature of space-time itself. When whatever produces the unexplained one-off burst does whatever it does, it releases more energy in a millisecond than our sun releases in days, channeling that energy into a beam of coherent radio emission that travels across billions of light years to land, improbably, in our receivers. These are not just astronomical curiosities. They are probes of physics at its most extreme, messengers from regimes where matter and energy and space-time behave in ways we can only approximate with our equations and our simulations. Every burst that arrives carries information about those regimes, encoded in its timing, its spectrum, its polarization, its dispersion. The universe is sending us data about itself, constantly from every direction, at every moment. We are only now learning to read the messages. Consider what we have already learned, even in the absence of a complete theory. We have learned that coherent radio emission can be produced by astrophysical sources at power levels that dwarf anything in our previous experience. We have learned that the intergalactic medium, the thin plasma that fills the space between galaxies, leaves measurable imprints on the signals that pass through it. We have learned that magnetars, those city-sized magnets spinning in the void, are capable of behaviours we had not anticipated, outbursts of radio emission that accompany their X-ray flares and gamma-ray flares. We have learned that the universe contains more neutron stars, more magnetaires, more exotic compact objects than we had fully appreciated, that the population of extreme sources is larger and more diverse than previous surveys had suggested. We have learned that our instruments, pushed to their limits, can detect signals from sources billions of light years away, that the faintness of the cosmos is not always an obstacle, that some phenomena are bright enough to be seen across the entire observable universe. These lessons will outlast the mystery. When the question of what causes fast radio bursts is finally answered, when the textbooks are updated and the Nobel speeches are given, and the discovery becomes routine knowledge, these broader lessons will remain. The techniques developed to find and analyse bursts will be applied to other transient phenomena. The instruments built to detect them will be repurposed for other surveys. The statistical methods refined to distinguish between models will become standard tools. The mystery is scaffolding, and when it is removed, a permanent structure will remain. Science advances not just through answers, but through the capabilities developed in pursuit of answers. The pursuit of fast radio bursts has already changed radio astronomy, has already expanded what we know how to do, has already created infrastructure and expertise that will serve other purposes long after this particular question is resolved. But let us not rush to that resolution. Let us instead rest here, in the uncertainty, in the middle of the story, where the question still hangs open and the possibilities still multiply. There is something valuable about this moment, something that will be lost when the answer arrives. Right now, the universe is genuinely surprising us. Right now, we don't know what to expect when the next burst arrives. Right now, the data could point anywhere, could reveal anything, could overturn assumptions we did not even know we were making. This is the rarest and most precious state in science, the moment of genuine not knowing, when the unknown is not a gap in the textbook but a live and active presence, when researchers go to work each morning aware that the day's observations might change everything. Savour this uncertainty. It will not last. The instruments are too good, the data too abundant, the researchers too dedicated. Within a decade, perhaps sooner, the mystery will be substantially resolved. The textbooks will be written, the lectures will be prepared. Students will learn about fast radio bursts the way they learn about pulsars and quasars and gamma ray bursts, as established phenomena with known causes and well-understood properties. The wonder will not vanish entirely, but it will shift, will become the wonder of understanding rather than the wonder of mystery. Both kinds of wonder are valuable, but they are different, and the transition between them happens only once. So let us sit with the mystery a moment longer. Let us picture the universe as it truly is, not as a static backdrop, but as an active environment, crackling with signals, humming with radiation, pulsing with energy across every frequency and every wavelength. The space between galaxies is not empty, but threaded with plasma and magnetic fields, with cosmic rays and background radiation, with the faint glow of ancient light and the sharp flashes of recent catastrophe. Into this environment, thousands of times each day, somewhere in the cosmos that we can see, a magnetar flares or a neutron star collapses or some exotic process activates, and a burst of radio emission begins its journey outward at the speed of light. Most of these journeys end in obscurity. The universe is vast and our instruments are small. A burst that originates in a galaxy 3 billion light-years away, travelling through the intergalactic medium, dispersed and scattered and attenuated, arrives at Earth as a whisper against the background noise. If no telescope happens to be pointed in that direction, if no receiver happens to be tuned to that frequency, if no algorithm happens to be searching for that particular pattern, the burst passes unnoticed. It washes over our planet and continues outward, travelling forever into the expanding universe, carrying its information to destinations that may never exist, to civilizations that may never arise, to instruments that may never be built. But some bursts find us. Some of them, by the pure statistics of pointing and timing and sensitivity, arrive at moments when our instruments are ready, when our algorithms are watching, when our researchers are awake and attentive. These bursts become data. They become papers. They become entries in catalogues and points on graphs and fuel for theories. They become the evidence on which our understanding is built. And each one of them is a gift. Each one is a message from a process we do not fully understand, a dispatch from conditions we cannot replicate, a piece of information about the universe that we could not have obtained any other way. The Manitere in our own galaxy gave us one such gift, a burst that was close enough and bright enough and fortuitously timed enough that we could see it in multiple wavelengths, could confirm its origin, could begin to unravel the connection between radio flashes and X-ray activity. The repeating sources have given us other gifts, patterns of recurrence that constrain the models, that rule out the catastrophic scenarios, that point toward long-lived engines capable of multiple outbursts. The one-off bursts have given us still other gifts, hints of diversity, suggestions of multiple source classes, evidence that the phenomenon is broader than any single explanation. The universe is generous with its signals. It is we who must learn to receive them. And this brings us, finally, to the deepest question of all. Not what causes fast radio bursts, but what they tell us about the nature of the cosmos we inhabit. Because these signals, whatever their ultimate origin, are reminders of something we often forget. The universe is not silent. It is not still. It is not a museum of frozen objects separated by empty space. It is alive with activity, with processes unfolding constantly, with energy being released and transformed and transmitted across distances that beggar the imagination. We live inside a dynamic environment, a cosmos that is always changing, always evolving, always producing new phenomena for us to discover if we have the wit and the patience to look. Fast radio bursts are simply the latest in a long sequence of such discoveries. A century ago, we did not know that galaxies existed beyond our own. 70 years ago, we did not know that the cosmic microwave background radiation filled all of space. 50 years ago, we did not know that gamma ray bursts were even a thing. that the universe routinely produced the most energetic explosions since the Big Bang itself. 30 years ago, we did not know that exoplanets were common, that nearly every star in the sky hosts at least one world. 20 years ago, we did not know that fast radio bursts existed. What will we discover in the next 20 years? What new signals are waiting to be detected? What new phenomena are waiting to be named? What new mysteries are waiting to be posed? The universe is larger than our imagination. It contains more than we have conceived, and every time we build a new instrument, every time we look at a new wavelength, every time we process the data in a new way, we find something unexpected. This is not failure. This is not a sign that our theories are wrong or our methods are inadequate. This is the fundamental nature of inquiry. We are finite beings trying to understand an infinite reality, and the disparity between our minds and the cosmos guarantees that surprises will never stop coming. Fast radio bursts are one such surprise. Whatever causes them, they have already taught us that the radio sky is more dynamic than we knew, that nature has found ways to produce coherent emission at scales we had not imagined, that the universe is full of engines and processes and events that occur constantly, everywhere, all the time, whether or not we are paying attention. This lesson will remain true even when the specific mystery is solved. This lesson is perhaps the most important thing the bursts have given us. So let the signals continue to arrive. Let the telescopes continue their patient watch. Let the data streams flow, and the algorithms search, and the researchers puzzle over each new detection. The answer will come when it comes. The mystery will resolve when it resolves. And in the meantime, every burst that registers in our instruments is a confirmation that we are not alone in a dead universe, not isolated in a cosmos of inert matter and empty space, but embedded in something vast and active and strange, something that we are only beginning to understand. Picture it one last time. It is night where you are, or perhaps approaching night, or perhaps you have left the daylight world behind and entered the quiet hours when the mind drifts and the body settles into rest. Above you, invisible through the ceiling, through the roof, through the atmosphere, the radio sky is flickering. Signals are arriving from every direction, from sources near and far, from pulsars keeping their metronomic time, from galaxies humming with the collective emission of billions of stars, from the cosmic microwave background painting the sky with the afterglow of creation itself. And scattered among all this, unpredictable and brief, bursts are arriving from the distant universe, flashes of radio light that crossed billions of light years to reach this moment, this place, this world. Some of them are being detected right now as you listen, as you rest, as the night deepens around you. Somewhere on Earth, a radio telescope is recording data, an algorithm is analysing the stream, a detection is being flagged for human attention. A researcher will look at the signal tomorrow, will measure its dispersion, will estimate its distance, will add it to the growing catalogue of cosmic messengers. The mystery will advance by one more data point. The answer will draw imperceptibly closer, but the answer is not the only thing that matters. The signals themselves matter. The act of detection matters. The knowledge that we are listening, that we have built instruments capable of receiving messages from across the universe, that we are paying attention to what the cosmos chooses to send. This is a remarkable thing. This is a kind of participation in the universe's own activity, a joining of our awareness to the events unfolding in the distant reaches of space and time. The bursts do not know we are listening. The magnetars do not care that their flares are being recorded. The colliding neutron stars have no awareness that their final moments are being studied by creatures on a small world, orbiting a modest star in an ordinary galaxy. The universe proceeds according to its own logic, indifferent to observers, unconcerned with understanding. But we are here anyway. We are watching anyway. We are trying to understand anyway. And that effort, that stubborn insistence on making sense of what we see, is something precious and strange. A phenomenon as unlikely in its own way as the bursts themselves. Perhaps that is the final message of fast radio bursts. Not any particular answer about magnetars or neutron stars or emission mechanisms, but a reminder of our own improbability, our own strangeness, our own participation in a cosmos that did not need to produce beings capable of wondering about it. The signals travel for billions of years across unimaginable distances, carrying information about events we cannot witness directly, arriving at a world where evolved primates have built metal dishes and silicon computers and mathematical theories to receive and interpret them. The whole chain of events from stellar collapse to conscious understanding is so unlikely, so contingent, so dependent on countless accidents of physics and chemistry and biology, that it approaches the miraculous. And yet here we are. Here the signals are. Here the mystery remains, tantalizing and open, inviting further inquiry, promising eventual resolution. The universe is speaking in its fashion, and we are learning to hear. Let that settle. Let the uncertainty be comfortable rather than troubling. Let the not knowing be a form of anticipation rather than frustration. The answer will come. The signals will continue. The instruments will listen. The researchers will wonder. And you, resting now in the quiet hours, are part of this too, part of the species that looked up and asked questions, part of the civilization that built telescopes and launched satellites and wrote papers and gave lectures and slowly, painstakingly across generations, assembled an understanding of the cosmos it inhabits. The fast radio bursts are still arriving. They arrived while you were listening. They will arrive while you sleep. They will continue arriving long after this night ends, long after this year passes, long after you and I and everyone we know has returned to the elements from which we came. The magnetas will flare. The neutron stars will collide. The exotic processes, whatever they are, will continue their work. And some future generation, equipped with instruments we cannot imagine and theories we have not conceived, will look back at this era as the time when the mystery was first posed, the time when the signals were first detected, the time when the question was still open and the wonder was still fresh. We are the generation of the question. They will be the generation of the answer. Both generations are necessary. Both moments are valuable. And the signals connect them, travelling across time as well as space, linking the events of the ancient universe to the understanding of the far future. For now, the signals are enough. The mystery is enough. The universe, vast and active and strange, is enough. Let the night deepen. Let the radio sky flicker with its invisible messages. Let the cosmic messengers continue their journeys across the dark. Somewhere out there, right now, a magnetar is about to flare.